Hello everyone, today we are going to talk about Ferranti effect. We will discuss its definition, causes and effects. Ferranti effect is the phenomena where the receiving end voltage of a long transmission line becomes higher than the sending end voltage under light load or no load conditions. Its causes include that due to the line's capacitance, the charging current is dominating over the small load current, and under light load, the capacitive charging current leads the voltage by 90 degrees, causing a rise in voltage. The following circuit diagram represents a long transmission line. We have the sending end voltage, we have the receiving end voltage, we have the sending end current, we have the receiving end current, and it's equal to 0. So in this case, the sending end current equals the charging current. We have the line's resistance, inductance and capacitance as well. In the following phasor diagram, we can see that the receiving end voltage is represented by the line OA, and there is a charging current represented by AB, and is leading the receiving end voltage by 90 degrees, and there is a voltage drop across the line's inductance represented by the line CB, and you can see that the sending end voltage represented by the line OC is shorter than the receiving end voltage line, which is represented by OA. Here the following equation represents a long transmission line. The sending end voltage equals A times the receiving end voltage plus B times the receiving end current. Under no load, the receiving end current would be equal to 0, and we will have the receiving end voltage at no load. By replacing the receiving end current with 0, the sending end voltage would be equal to A times the receiving end voltage at no load. We will have that the magnitude of the receiving end voltage at no load would be equals to the sending end voltage divided by A, and A is less than unity, and it means that the receiving end voltage will be bigger than the sending end voltage. We will talk about its condition right now. So it's more noticeable in long high voltage transmission lines, usually above 200 kilometers. It occurs mostly during the light load or no load operations, and its effects including that the receiving end voltage is bigger than the sending end voltage, and it can cause over voltage at the load side, which may damage equipment. To mitigate this phenomena, we should use shunt reactors at the receiving end to absorb excess reactive power. We can install FACTS devices, and we can try to operate lines closer to their designed load. In this simulation circuit, we have a long transmission line, and it's represented by a Y model. We have the sending end voltage, which has an amplitude of 500 kilovolts. We have a frequency of 50 Hertz as well. We can see the line's capacitance, inductance and resistance as well. And on the right, we can see the load. It has a resistive and inductive components. And let's have a look on the sending end and receiving end voltages at no load. So we can see that the receiving end voltage is 420 kilovolts, while the sending end voltage is 350 kilovolts. So the receiving end voltage is a lot higher than the sending end voltage. Let's have a look right now under the load condition, where when the load is connected to the system. We can see that the receiving end voltage is equal or very close to the sending end voltage. The receiving end voltage is 340 kilovolts, while the sending end voltage has a value of 350 kilovolts. So like they are almost the same. Maybe there is a voltage drop here on the transmission line, but if we brought back the system to the no load condition where the receiving end current is 0, we can see that the receiving end voltage will come back to a very high value of 420 kilovolts, while the sending end voltage is 350 kilovolts. So we can see right now that in very long transmission lines, under no load condition, the receiving end voltage would reach in extreme high values, which you can call the equipment damage.